All right, ladies and gentlemen, welcome to today's webinar, Is Climate Change Real? For those of you who are joining us for the first time, welcome. We're thrilled to have you here with us today. For those of you who have been following our now fourth part to the series, JNF Canada has done a four-part series on climate change, and today we are lucky to have Professor Colin Price joining us to debunk for those who still believe that climate change is not real. Before we get started, there's a few faces that I would like to acknowledge who are here with us today. We have the Executive Director of JNF Montreal, Quebec region, Galit Levy, here with us today. We are also joined by the Executive Director of the Canadian Friends of Tel Aviv University, Sharon Frankel, who is here with us today. Thank you, Sharon, for being here. And of course, this whole initiative could not have been possible without a pillar and leader in our community, Jeff Hart, who is also JNF Montreal's Negev honoree. So Jeff, thank you for being here with us today. Before we get to the reason we're all here, I'd like to introduce everybody to Karen Aflalo, the president of JNF Montreal, who will start off with some opening remarks. Karen.
Mute.
Yes, I was muted. Sorry, guys. Hello, everybody. So it's my pleasure to welcome everyone this afternoon to the fourth installment of JNF's Canada Special Climate Change web series. Today's event is being brought to you thanks to JNF's wonderful partnership with Tel Aviv University, especially due to the support and assistance of Sharon Frankel, who Phil just introduced. He is, as Phil mentioned, the Executive Director of Canadian Friends of Tel Aviv University for Ottawa, Quebec, and Atlantic Canada. So thank you very much, Sharon. Over the course of our web series, we have been privileged to hear from some fascinating minds, including Laura Faye Tenenbaum, a renowned former NASA scientist, Dr. David Fisman and Dr. Jacob Moran-Gilad, two top pandemic researchers who addressed how COVID-19 and future pandemics will be affected by climate change. And more recently, Israel's Minister for Science and Technology, Itzhak Shai, who shared some of Israel's research and development in combating the issue. Today, we're thrilled to welcome Colin Price, who is a professor of atmospheric sciences in the Department of Geosciences and head of the Porter School of Environmental Studies at Tel Aviv University. Professor Price was born in Johannesburg, South Africa. And after starting his university studies there, he transferred to Tel Aviv University in 1982, where he completed his BSc and Master's in Science degrees in Geophysics and Atmospheric Sciences. He received his PhD at Columbia University, New York in 1993, while working at NASA's Goddard Institute for Space Studies in New York. After completing a postdoctoral fellowship at the Lawrence Livermore National Laboratory in California, he returned to Israel and joined the faculty of Tel Aviv University in 1995. He has published more than 140 scientific papers and has a team of over 10 graduate students and researchers working under his guidance on various scientific research projects. He heads the Institute on Innovation in Transportation and the Institute on Nanosatellites, both at Tel Aviv University. Before I give the floor to Professor Price, please remember that you could always send your questions in the chat box, and Phil will do his best to address as many of them as possible during the Q&A session. So without further ado, Professor Price.
Thank you. Great, can you see my screen?
We see it.
And you can hear me too.
We can hear you.
Great, so thank you, Karen, for the introduction, and thank you for inviting me to come and speak to you. So this is a somewhat controversial title, Is Climate Change Real? And I'll start out already by answering the question, and the answer is a big yes. In fact, I think more than 90% of the scientists working in this field of climate change, meteorology, atmospheric science, all agree that climate change is real, it's happening, we can see it's happening. Maybe less are convinced that we're the cause of this climate change, but definitely the climate is changing and very dramatically. Now, I like to start this presentation by showing this picture of the globe, the Earth with a fever. And I like to compare it with our bodies. When we have a fever, normally when we're healthy like today, the temperature of our body is 37 degrees. Excuse me. When we have a fever, it goes up by 1 degree, 2 degrees. If we have a 3-degree fever, we're maybe in hospital. 4 degrees, we could be dead, actually. Well, the Earth also has a fever at the moment, but unlike our body temperature, which is 37 degrees, the Earth's temperature, the average temperature, is 15 degrees. So a 1 degree warming or a 2 degree warming of the Earth relative to 15 degrees is much more significant than a 1 or 2 degree warming of our bodies relative to 37 degrees. Now, if we look at the temperature, the actual data, the thermometer data of the global warming from 1850 until 2017, what we see here is the 0 is not 0 degrees. This is a reference of the temperatures, the average temperature of around 15 degrees, which is the average between 1951 to 1980. And what we see with the red dots, sorry, which is the average of all the data from all the weather stations all over the planet. In 1850 and 1860, it was about 0.4 degrees cooler than the 1950s, 60s, and 70s. And today we're nearly 1 degree warmer than the 1950s, 60s, and 70s. We can also see these vertical lines, which represent the uncertainty we have in this data. We can't measure everywhere on the planet because a lot of it is covered in oceans. We don't live everywhere. We don't live in the middle of the deserts. And so there is uncertainty with this data. But as we get actually closer to the present, we have less and less uncertainty. We have better data. We have satellites. We have better instrumentation. And the estimate, the best estimate by all the researchers, is that we have on the order of 1 degree warming in the last 100, 150 years. And this is the fever we're talking about that the Earth has. About a 1 degree fever in the meantime. And I'll show later that the predictions are for this to go up another few degrees maybe by the end of the century. The worrying fact is that if we look at the last few years, when we have the best data, we have the warmest temperatures. We're keeping to break records every year, 2016, 19, and likely this year, 2020, we're going to break records in global temperatures. The 15 warmest years we've had on record have occurred since the year 2000, and every decade is warmer than the previous decade, at least in the last 100 years or so. So something is definitely happening. Now that was global mean temperature, getting one number for the whole planet. If we look now regionally, we can see here each panel is for a different decade, the 1970s, 80s, 90s, and the 2000s. The colors again represent the changes in temperature relative to this reference of 1951 to 1980 over this 30-year period. So we have here we have negative numbers and positive numbers. The blues and greens are if it was cooler in that decade relative to the 1950s, 60s, and 70s. And where it's orange and red, it's warmer than it was in that period. And we see that every decade we're getting more and more oranges, yellows, reds, implying that more areas of the planet will be becoming warmer relative to the 1950s, 60s, and 70s. But something important we see here is that even in the last decade or two, there are regions where over the whole decade we see blues or greens, implying that those regions were actually cooler than the 1950s to 1980s. And so when we have a particularly cold winter in Canada or the US, that doesn't necessarily mean that the whole globe is not warming. When we're talking about global warming, climate change, we're talking about the whole planet. So it's possible that we can have a very cold winter in some place on the planet, but in other places it could be a lot warmer. And when we take the average, we're still seeing the globe is getting warmer. And 70s. And the size of the circle and the color represent how much it's cooled or how much it's warmed relative to the 1950s and the 1980s. And you can see as we go into the year 2000s, and this will end in 2017, all the countries of the globe are warmer than the 1950s, 60s, and 70s. Israel is 1.1 degree warmer than that, and Canada up here is 1.5 degree warmer. And remember that over the whole century, we had globally about a 1 degree warming. And here we're seeing more than a 1 degree warming in about 50 years. So in Israel and in Canada, we're seeing double the warming than we're seeing on the whole planet. If you don't believe the data, just look out the window. Here we can see some images from Alaska, 2004 relative to 1919. This huge ice glacier and ice sheet has disappeared. This is actually an image from Canada showing 1941 compared with 2004. Same location, the photograph, and this huge glacier has disappeared, and we can see the end over here. This white region on the image is actually where the ice used to be, so you can see how thick this ice was in that region. 95%, if not 99%, of all the mountain glaciers around the planet are receding or getting smaller, and the only explanation is that things are getting warmer. So how do we explain this? Well, first of all, we need to talk a little bit about the greenhouse effect. The greenhouse effect, which I'm sure you've heard about, is called the greenhouse effect because the atmosphere, Earth system, acts a little bit like a greenhouse. It's not the perfect comparison, but when we have a greenhouse, we've got windows of glass or plastic. They let the sunlight in, which warms up the surface and the plants, and the heat is trapped inside. If we open the window, we can let some of the heat out, but it's a lot warmer inside the greenhouse than it is outside. Well, the atmosphere of the Earth acts kind of like the windows of the greenhouse. It lets the sunlight in, but the heat, after heating the surface, the radiating heat doesn't all go out into space, and some of it gets trapped inside the atmosphere, just like in the greenhouse. And the truth is that without the atmosphere of the Earth, the temperature, the average temperature of the Earth would be minus 18 degrees C and not plus 15. The oceans would be a solid block of ice, and you and me wouldn't be sitting here talking to each other today. Life wouldn't have evolved on planet Earth if we didn't have an atmosphere. So the atmosphere acts like a blanket, and it warms us up from minus 18 to plus 15, 33 degrees C, because of the atmosphere. And in fact, it's only really due to water vapor in the atmosphere, not necessarily oxygen or nitrogen, which are the other gases, but I don't want to go into too many details there. So at the moment, we're now adding to that greenhouse. We're adding more blankets onto the atmosphere, and we're causing what we call a man-made greenhouse effect. Instead of water vapor, which is the main natural greenhouse gas, and greenhouse gas means these are gases which act like the windows of the greenhouse. They trap in the heat, act like a blanket. The main increase we're seeing now are in other gases. Mainly, most people talk about carbon dioxide, which is more than half the problem, but there's also methane, CFCs, ozone, nitrous oxide. And here we can see on the sides the increases that we've seen in the last decades in all of these gases. And the reason we believe these are increasing is simply because of our activities here on planet Earth. Mainly the production of energy. We need energy for our electricity at home, for our cars, our transportation, but also to produce our food. So agriculture is also a factor. Industries, all of our activities which involve production of energy use at the moment mainly fossil fuels, and these produce carbon dioxide, also methane from agriculture. And so this increase we're seeing in these greenhouse gases in the last decades, if not 100 years, we believe is basically because of man-made activity here on the planet. Now you can say, well, how do we know that? How do we know that what we're seeing now, this increase, isn't something natural, just a natural fluctuation of the climate? We've had ice ages before, we've had warm periods before. How do we know really what we're seeing now is really anomalous? Well, in order to go back and see what happened in the climate thousands of years ago, we have to find various scientific methods to look and to study the climate, what we call paleoclimate, the ancient climate. And one of the key methods is using ice cores. And here you can see these scientists holding these ice cores. You can see one lying down here. And there are only two main ice sheets left on the Earth today, in Antarctica and in Greenland. In Antarctica, we have about 4 kilometers thick ice until we hit the bedrock. In Greenland, it's about 3 kilometers. And how does ice form? Snow falls and eventually gets compacted. When we have maybe 150 meters thick snow, it's heavy enough to cause the snow to form ice underneath it. Now, something interesting happens when ice forms naturally. You have bubbles of air between the snow, which get trapped inside the ice. And those bubbles of air in the ice have the concentration of the gases in the atmosphere at the time that that ice formed. So if that ice formed 10,000 years ago, and we carefully open it today, we can see what was in the atmosphere 10,000 years ago. So that's what we can see on this plot. This is going back 2,000 years. And you can see the little bubbles, the little white dots are the bubbles of air inside the ice. And here we can see the concentration in the different colors of carbon dioxide, in methane, in nitrous oxide. In the last 2,000 years, we're around about here. And we can see that they're all fairly stable, small wiggles, and then all of a sudden, boom, they all took off and they keep on going up as we noticed today. But they all started going up at the same time, and they've all gone up dramatically in the last 200 years, 300 years, compared with what we see for 2,000 years. Now, we can also get an estimate of the temperature in the past. The thermometer measurements we only have for about 150 years, and that's shown in the red curve here. But we have various methods using tree rings, pollen, sediments in lakes and in the oceans, the ice cores again, corals using what we call isotopes, whether oxygen isotopes or carbon isotopes. And we can get an estimate of the temperature of the Earth relative to today. So we don't get the absolute temperature. But if today 0 is the temperature more or less in the 1950s, 60s, and 70s again, we can see the temperature relative to that. And what we see if we go back 1,000 years using these different methods, we were actually in a slight cooling stage. We were actually going down to the next ice age in another 80,000 years. And then all of a sudden something happened and we see this change in the trend, the increasing temperature. And if we continue this today, 2019, we're up here off the chart already. Again, the blue envelope here represents the uncertainty we have in the data. So the temperatures we see today and in the last decades are definitely the highest we've seen maybe in the last 1,000 years and likely longer. But we can go even further back. Here we can see 420,000 years of history of the climate of the Earth. 0 is today, and going back 420,000 years, and what we see here is the temperature. This is measured again from the ice cores and from using chemical isotope methods. Again, relative to today, so 0 is today's temperature. We have in the blue carbon dioxide in the bubbles of the ice cores, and in pink we have the methane in the bubbles. First thing we see is that there's some periodicity here. There's a up and down warm periods, which are even warmer than today, 2-3 degrees warmer than today, and these cold periods, which we call the ice ages. The last ice age was 20,000 years ago, around about here. The whole of Canada was underneath ice, and even the Great Lakes and New York City was under 2 kilometers of ice. And this was the last ice age, and we see that every 100,000 years, more or less, we've had ice ages. We understand what produced this is related to the orbit of the Earth around the sun, the shape of the ellipse, which changes over 100,000 years. But what we also see here is that the warm periods are the periods where we have high concentrations of greenhouse gases in the atmosphere. And the opposite, the ice ages, are where we have the minimum amount of greenhouse gases. And so we're fairly confident that periods with high concentrations of greenhouse gases are generally warm periods on the Earth, and the opposite for the ice age. Well, where are we today? If we put today's data, you can see these arrows on the side, we're off the chart. If we look just at the carbon dioxide in blue, throughout the last, say, million years, this is only 420, but I can bring you a lot more data, the highest concentrations of carbon dioxide in the atmosphere have been around about 300 of these units, 300 parts per million. Today, we're up here, around about 415 in July 2020. Way off the plot, and this has gone up just in 200 years. If we look at the methane, the highest values of methane in the last million years have been at maybe 800 of these units. We're up here now at 1,800, completely off the chart of the methane. So something dramatic is happening on planet Earth. And if you talk to anyone, any skeptic, anyone who doesn't believe in climate change, whether it's real, they cannot explain this. There's nothing natural which happened on planet Earth to cause such dramatic increases in greenhouse gas. The only reason is the Industrial Revolution and the population of planet Earth. And that's what we can see here. This is basically the last 10,000 years, the number of people living on the Earth. And we can see that until the Industrial Revolution, a few hundred years ago, we had less than 500 million people on the planet, in maybe even 250 million. And within 200, 300 years, we've jumped from about 500 million to more than 7.5 billion people on the planet. And although there were many good things which came out of the Industrial Revolution, we had machinery, we could farm not only for our family, but for the whole village, for the whole town. We got medication, vaccines, the life expectancy increased, so many good things came out of that, but some bad things too. The bad things were that we were starting to use too many resources, burning of fossil fuels, which got our economies going, and this resulted in the dramatic increase in greenhouse gases in the atmosphere. And now we're starting to see the impact on the global climate. So what's predicted for the future? Well, when we want to see what may happen in the future as a result of these dramatic increases in greenhouse gases, we have to use these computer models. These are not physical models. These are models of millions of lines of codes in a computer. And we try to, first of all, simulate what we know today of the climate. We need to divide the globe up into boxes or grid boxes like pixels you have on your digital camera. And in every pixel, we have to try to solve all the processes which occur both in the atmosphere, whether this is winds or cloud formation or rain formation, also in the oceans, the currents in the ocean, temperatures in the ocean, how the sunlight interacts with gases and particles in the atmosphere, the vegetation, snow cover, extremely complicated. And this has to be calculated in every single box on the planet. And then we have to also calculate how the winds are going to transport pollutants from place to place, how the oceans may absorb the heat and even the carbon dioxide. And all of this has to be done simultaneously. And if we want to see what may happen in 50 or 100 years, then we have to run these models for months at a time, in our time, in order to get results. Extremely complicated, huge computer power needed and manpower. And therefore, there are only about 30 groups in the world which run these models. And these models are used then for the reports which are published by the United Nations. So you may have heard of the IPCC, which comes out every 6 or 7 years with the state-of-the-art information from maybe 2,000 scientists which work on these reports. We're working on the next report at the moment. There should be a report within a year or two coming out with the latest data and the information and knowledge about climate change, which you'll hear about probably in the next year or two on the news. So what's predicted for the future? So the first thing is that the planet's going to warm. So here we can see from 1990, the simulations giving the range of forecast into the future. Now, what happens in the future depends on what we do. The upper boundary here is what we call business as usual, implying we basically don't do anything. We keep on doing what we're doing today. If we really decide to go to renewable energies, to reduce fossil fuels, carbon sequestration, many other technologies, then maybe we'll be closer to the bottom here. And so there are different colors or different scenarios for the future. But we can see that the estimates are between around about 2, 3 in the middle of the road, 2, 3 degrees by the end of the century. Not going to stop there unless we do something. But there are some scenarios even which say maybe 5, 6 degrees by the end of the century. If you remember that the last ice age, it was about 5, 6 degrees cooler than it is today, but that took 20,000 years, that change. Here we're talking about 100 years and going in the opposite direction. You may have heard of Paris 2015, the Paris talks. Well, the idea was there to limit the warming to 2 degrees relative to the pre-industrial. By 1990, we already had 0.5 degree warming, so it's another 1.5 degrees. And so depending on the scenarios, we may pass that threshold as early as 2030 or 2035 if we keep on going at the rate we're going. If we're optimistic, maybe we have until about 2060 before we pass that threshold. But most people don't notice such a small change in 2, 3 degrees in the mean temperature. If we look at this distribution, say this is the temperature in Montreal, So we have most of days are around about the mean. We have some very cold days, we have some very hot days. If we shift this whole distribution by 1 or 2 degrees, most people don't notice the mean, the change in the mean. What we do notice is the very warm days. We get many more warm days than we did before. And we also have heat waves and extreme temperatures, which will break records, which we never had before. And this is what the public actually feels. Well, if we look at the actual data, this is happening. What we see here, this is real data for the different months of the year, January to December, taken 100 years apart. So in blue, we can see the distribution of temperatures for 30-year period, 1881 to 1910, compared with 100 years later, 1981 to 2010. And this is relative, again, to the temperatures of 1951 to 1980, a 30-year period, the zero here. So we can see that the temperature distribution has shifted over 100 years, has gone approximately 1 degrees to warmer temperatures. The shape of this distribution has also changed, which is also interesting. And the last few years, if we plot them here, 2016, 17, we can see they're breaking all the records again. So they're way out here on the right-hand side. This plot needs to be updated from 2017, but basically the last few years we're breaking all the records once again. So again, climate change is real. It's happening. The data shows that it's happening, and it's not just happening in the future. It's already happened, and we can see it at the moment. How does that affect us personally? Changes in this distribution? Well, let's look at an example from the heat wave in Europe in 2003. Here we can see the distribution of temperatures in Switzerland from 1863 to 2003. Every line here is 1 year. The mean was in Switzerland around about 17 degrees C in the summer months. And in 2003, it was out here above 22 degrees, 22.5 degrees, a shift of about 5 to 5.5 degrees in the mean. Well, in Israel, this would still be fairly pleasant temperatures, but people aren't necessarily used to these extreme temperatures in Europe. And in 2003, in less than 2 weeks, in about 11 days, more than 70,000 extra people died. If you compare that to the year before, for the same 10 days, the year afterwards, 70,000 extra people died from this heat wave, mainly in France, also in Spain and in England. And this is because they're not prepared for this. The people are much more vulnerable to heat waves, say in Europe or in Scandinavia, than we are, say, in Israel. And the vulnerability is where climate change is really going to impact the populations around the globe. In Paris in 2003, there were very few air conditioners in hotels. They didn't expect such heat waves. Today it may be different, but you have to adapt to these changes if you want to actually survive it. In addition to temperature, all of the models by the end of the century predict changes, quite dramatic changes in rainfall patterns. But here, some places will get drier and some are going to get wetter. On the left, we can see the predictions for December, January, February, Northern Hemisphere winter, June, July, August, Northern Hemisphere summer, where the browns are decreases in rainfall up to about 20%, and the blues are increases of up to 20%. Should point out that the Mediterranean, especially Israel, our rainy season is December, January, February. The models predict up to about 20% decrease in rainfall. We're seeing this already across the Mediterranean, Spain, Greece, Portugal, Italy, dramatic decreases in rainfall. And what's also worrying here is these little black dots on the plots show where 90% of the climate models, the simulations, agree with each other, implying we have a lot more certainty in these results compared with the areas without the black dots, where those are simple averages of all the models, but some are going up, some are going down. In Canada, you can expect a lot more rainfall and maybe extra flooding in higher latitudes. And so areas which are actually moist today are expected, according to the models, to get more rainfall, and areas in the subtropics which are dry are expected to get drier. And this too, we seem to be seeing already. California drought, 2011. We also heard about Cape Town, where the taps nearly went dry of water. And in other regions like Pakistan, in China, we're seeing these massive flooding events, which are becoming more and more frequent. The bottom line for rainfall is that we can see the hydrological cycle is going to become more extreme. Some places it's going to get much drier, more drought. Other places it's going to become much wetter with flooding. And the third final parameter I want to talk about that models predict is sea level rise. In fact, in 2000, with the United Nations IPCC report, predicted less than a half a meter rise in sea level globally by the end of the century. As soon as they published that report, because of new research about the melting of Greenland, they changed that, and now the estimates are up to about 1 meter global sea level rise by the end of the century. Now, if we look at the predictions from even earlier, 1990s, and the gray area shows the predictions of the UN report for from 1990, and then we can check that relative to the actual observations. In the blue, you can see the real observations of sea level rise which have occurred from 1990 to 2010. And what we see is that they're at the upper limit of what all the forecasts gave, implying that the scientists actually may be underestimating most of their forecasts. It may be a lot worse than we actually say it's going to be. What's the meaning of a 1 meter sea level rise? Well, let's look at our neighbor here in Israel. If we look at Egypt, the Nile Delta, you can see what will be underwater for just 1 meter sea level rise. Alexandria, Port Said, all of this is going to be underwater for a 1 meter sea level rise. And that implies 6.1 million people need to be removed and they have to find new homes. This is also 4,500 square kilometers in croplands, agricultural land. And this is very worrying because this leads to what people are talking about, climate refugees. If you have 6.1 million people who need to find a new home, and there's also not much food, and the population is going to be growing anyway in Egypt, it's possible that some of these refugees may make it to the southern border of Israel. So 3 key parameters are going to change in the future. Temperatures are going to go up, sea level is going to go up, and rainfall, precipitation is going to change. Some places are going to get drier, some places are going to get wetter, but it's definitely going to change. Even the length of the rainy season, which is important for agriculture in many developing countries. But just these 3 parameters have major impacts on our health, whether we're talking about malaria or dengue fever, West Nile virus, agricultural droughts, pests, forests. I know in Canada there have been problems with the pine bark beetle in the west. Water resources, the quality, the quantity of water, coastlines because of rising coastlines, and biodiversity, natural habitats. In fact, this has got a lot more attention recently because of the COVID-19 pandemic, because some people claim that some of these viruses we're seeing these days in pandemics are because we're actually destroying habitats of exotic species in the tropics, and also global warming is causing them to migrate to cooler areas, and then they come into contact with domestic animals, which then come in contact with humans, and therefore we may actually see more of this in the future because of climate change. So let me just go back to this plot about the last 10,000 years. We call this period a geological period called the Holocene. The Holocene is the period that all of our civilizations, from the Greeks, the Romans, the Egyptians, all of our civilizations have developed on planet Earth. And before that, as I mentioned, we had the Ice Age, which the whole of Canada was covered in ice, down to New York, the whole of Northern Europe, Scandinavia, about 4 or 5 degrees cooler. The Holocene has been actually very stable. The temperatures plus minus half a degree, the Vikings, the medieval warm period, all of our cities have been built during this period. Our sea levels have been constant, so the coastlines have been constant. So we've had this period of 10,000 years, which has been actually very stable. And we're leaving this now, and we may actually go up 4 or 5 degrees in 100 years, not 20,000 years. And therefore, we're going to change the climate dramatically, change our coastlines dramatically, and things are going to be very different. People are calling this the Anthropocene, relative to the Holocene. Anthropocene, that this is the new geological period where people are basically ruling and influencing the climate of the planet. So, are there solutions? Well, yes, and I like this simple plot. It's very simplistic, actually, but basically it shows the problem and the solution. And this shows basically the cost of energy to you and to me. How much do we pay for our electric bill? How much do we pay for gasoline in our car? How much of our food costs go to paying for the energy that made that to the farms and for the animals? And what we see here, the blue curve is the cost of energy if we use fossil fuels, coal, oil, natural gas. And the green curve is the cost if we basically use renewable energies. And today we're somewhere around about here, where it's still quite expensive to buy electric cars, to put solar panels on our roof, and it's still easier to and cheaper to get energy from maybe coal plants in China. That's what they're using, or oil or natural gas we're using here in Israel. But eventually, the cost of oil and natural gas is going to have to go up when we run out of it. It may take 1,000 years, but I mean, theoretically, when it runs out, the price will go up. On the other hand, through innovation, the price of renewables is going to get cheaper. And this, we can look at the example with our smartphones. Our smartphones are much cheaper today than they were 10 years ago, and 20 years ago, we didn't even have them. So eventually, these two lines are going to cross. And when they cross, we're on the way to solving the problem. Because there's no reason why I would want to have polluted energy which is polluting the atmosphere, but it's more expensive than the clean energy. Why would I use it? And the main goal of me and you and our policymakers and our leaders should be to try to bring this crossing point closer to the present. The closer these lines, the sooner they cross each other, the sooner we can solve the problem of climate change. And the good news is that if we look at the cost of electricity from various sources, oil, nuclear, coal, gas, wind, photovoltaics, solar energy, the prices per unit energy of photovoltaics are dropping dramatically. And this coming decade, I think, is going to be revolutionary. We're going to see huge changes in technology, in regulation related to renewable energies. And this is actually some hope that we may be able to solve this problem in the coming decade or two. But in the meantime, we need to slow things down. We need to slow down the increase in greenhouse gases in the atmosphere. And just by efficiency, we can actually flatten the curve. People have been talking about flattening the curve of the COVID virus, but the same with the carbon dioxide. Just by increasing efficiency in buildings, the heating, the cooling, appliances that we buy at home, the lighting at home, the transportation, industry, we can actually flatten this curve and keep the greenhouse gas concentrations more or less constant into the next decades to give us time to find either the technological solutions or the policy regulation solutions. And yes, I do think that if we do have to use the fossil fuels, at least we should move to natural gas, which is the most efficient source of energy if we do need to still use fossil fuels in the meantime until we find other solutions. And that's the idea of the Paris 2015 agreement, to basically reduce emissions, to give us time to find the long-term solution. So with that, I'm going to end, and I'm just going to put up this slide, and this I show in high schools when I give talks, because people always ask me, well, what can I do? This is a huge, massive problem, but how can I really have any help or have any impact on this? Well, if everyone did a few of these little things, we would have a global impact. And so one person alone is not going to make the change, but if we all work together and we all do a few of these things, then definitely we can have an impact. So let's look at a few of these. Travel. The most polluting form of travel is actually flying. So if we could maybe take a train, if we were, say, in Canada, from one place to the other, or even drive our car, this may be better than flying. Obviously, we can't drive or go across the oceans without flying. In our car, we can buy more fuel-efficient cars. We can carpool. Just putting the right pressure of air in your tires will save energy. Obviously, walking, biking, taking public transportation will help. At home, changing our light bulbs to maybe LED, LEDs, or energy-efficient light bulbs. When we go and buy new appliances, get the most energy-efficient ones. Simply turning off the lights when we leave the room, and maybe using the sun to dry our clothes instead of the clothes dry. Solar water heaters like we have in Israel. When we go shopping for our food, buying fresh produce from a local market will reduce the energy that's needed for transportation or for freezing or for packaging. Anything we buy in the supermarket which is packaging, which is frozen, needed energy. So if we buy fresh foods, that reduces our energy footprint. Obviously, less junk mail. Today, most of the junk mail is in our email. Recycled paper for printing, cloth bags. Eating less beef and maybe meat as well, but beef is a big problem. We know that beef and cattle are huge sources of methane, but they also need a huge amount of water for every kilogram of beef, steak, hamburger we need. If anything, we should move maybe to poultry or other types of meat or fish. I don't like to tell people not to eat beef or not to eat meat, maybe a little bit less. So maybe instead of having beef every week, 1 week a month or so. But maybe the most important thing really is for us to be a catalyst. And what I'm doing tonight and this afternoon in your place is to talk about it, to speak to your family, to speak to your friends, speak to your leaders, your politicians. And next time you go to vote, try to vote for someone who realizes we have a problem with the climate and is also ready to maybe do things, maybe things which may actually hurt at the moment, but will give us some benefit in the long term. And so voting for the right people and having the right leaders is also very important in order for us to have an impact on the climate crisis in the future. So I think with that, I'm done. Thank you very much, and I'd be happy to answer any questions.
Thank you so much, Professor Price. So to answer the question that a lot of people emailed, a lot of people asked about, climate change, it's real. 150%, it is real.
Well, I hope we're wrong, but from all the research we've been doing, all the evidence, I mean, science is based on evidence, a collection of evidence, data, and there's a chance that all the scientists, or 90% of them, are wrong. I don't think so. There's enough competition between the scientists that they all want to be right, but the data is overwhelming that things, the greenhouse gases are the highest they've been at least 1 million years, if not longer. Definitely while humans have been walking around the way we know on planet Earth. The temperatures are going up at a very dramatic rate. The rate has never been seen before. So yes, climate change is real.
So we have a handful of questions, minimal amount of time. We're going to do our best to address as many as possible. First off, for those of you who are asking, this entire event will be posted online to the JNF Canada YouTube page. So if you missed anything, you want to go back and watch it, you want to share it, it will be posted at latest tomorrow. Feel free to check it out on YouTube at the JNF Canada page. Our first question comes from Larry. Today's world, you mentioned airplanes, our cars, cruise ships, all kinds of factors that cause climate change. What could have caused the ice ages and global warming before man exacerbated the problem?
Good question. So I mentioned that briefly, but we know there's something called the Milankovitch cycles. You can look online, Milankovitch theory. Basically, the Earth goes around the sun in the shape of an ellipse, not in a circle, a perfect circle. And that shape of the ellipse is affected by the gravitational pull of all the planets in the solar system and the sun. And so there are various orbital parameters which change on very long time scales. And the one which we think is related to the ice ages, which changes on 100,000 years, is the shape of this ellipse. It becomes more elliptic like an egg or more circular. And this influences how much sunlight we get at the Earth at the closest point to the sun on our orbit and the furthest point. And so when many of these factors come into play, what we really need for an ice age is for the summers to be cooler, because you want to keep the ice and the snow which is falling in the winter through the summer to build more and to get ice sheets, to grow ice sheets over time. And so in certain circumstances, based on the orbit, you can actually get less energy from the sun and it cools the climate slightly. And this is what produces the ice ages. The same thing when the orbit becomes a little bit more circular, you start to get more sunlight and this starts to melt them. And this will give us the warmer periods and these fluctuations which go backwards and forwards every 100,000 years. And if we weren't to interfere with this, as I showed you, we're actually on a cooling trend now. So we were on a cooling trend. And if we were not interfering with the climate, we should have gone in another 80,000 years. We're already 20,000 years since the last ice age. Another 80,000 years, we should have been in the next ice age.
So in 2020, people need to travel, not just to go on vacation, not just to go to Mexico, but there are uses for planes as far as transportation, medical transport, all these types of things. So planes are not going anywhere anytime soon. But is there a way to convert these planes so that they are more eco-friendly?
Yeah, so people are working on this, both on the fuels that we use for aircraft. The fuels are fairly inefficient, and even I think they've had first few pilot studies of solar-powered aircraft, not jetliners yet. But definitely there is a lot of work on trying to increase the efficiency of the use of the fuel, different fuels, what we call greener fuels. And it's possible that in the future we'll have electric planes, like we have electric cars, and those batteries will be charged maybe by solar energy. So it's possible that in the future we'll have electric planes. I think we have already small planes which run on electricity, which will have to have batteries in them, and those batteries could be charged with solar energy.
So you mentioned it in your presentation when you had the two graphs crisscrossing and how we need to get to that point sooner rather than later. And funny enough, I was on the golf course the other day and a friend of mine and we're talking, there was a house on the course having construction done. He's putting in solar panels, solar heat pumps, all these things. And for fun, we took out our phones, we Googled it. How much would it cost for me to change my house to all these solar heating? And the prices, I don't remember the exact number, but it was pretty high. You talk about, electric planes. If I want to go out and get myself a Tesla today, it's going to cost a lot more than me going out and leasing or buying a Nissan. How can they develop these electric, eco-friendly solutions, but still leave it that people like myself, like majority of the people in this room right now, have access to them? Because the answer to them will be, well, I can't afford it, so I have no choice but to take the cheaper, non-eco-friendly route.
Exactly. That's exactly the problem. So on the one hand, so this can be done through regulation. So the governments can put, first of all, they can put the real price on the fossil fuels. So they can charge you more for using a polluting car, and they can give you incentives and tax reductions if you do buy clean energy car or put solar panels on your roof. And so through regulation, this is possible. So this needs leadership from the governments to allow people subsidies, allow people tax deductions, but also we need the technology to get cheaper and improve. So we also need massive investment in research and development to produce the next more efficient solar panels, cheaper cars, which are running on electric batteries. So both the research and development needs massive investment, and I think this is happening in some countries, but also we see startup companies, for example, in Israel, which are going to this area because they see there's a huge market and they're going to make a lot of money if they can prove this. There's so research and development, but regulation is also important. And if we had some good leadership where they would allow people to buy or to, for example, how did the home mortgages start? These started in the after the Great Depression, 1929, 1930. People wanted a dream, but they couldn't afford it. So they developed mortgages where we'll give you a home today, but you pay it over the next 20 years. Well, it could be the same with electric cars. If the government could let you buy tomorrow an electric car and you pay it at very low cost in the next 10 years, people may do that. So again, we need regulation, we need policy at the governmental level, but we also need definitely more research and development to bring down the costs. As you can see with smartphones, the costs have dropped dramatically in the last 10, 20 years. The technology is much better, much smaller, much lighter, and that's just from innovation.
So you mentioned world leaders. I mean, there are world leaders, I'm not going to name them, that completely they say this is not true, this is not real, it's not happening. They also believe that COVID-19 is not really happening and it's going to clear up like the sniffles I had last week. But not just in those countries. You have China, who contributes to about 50% of the global pollution. How do you stop climate change when China, one country, is producing approximately 50%? And that question actually comes from Steve.
Yeah, well, actually, China is leading the way actually now on renewable energies. China has had a huge growth in the last 20 years and caused a lot of pollution. People can't breathe, or until COVID, they couldn't breathe on the streets of Beijing. And so they realized actually that they got to change. They can't continue this way with fossil fuels because the people are dying in the streets from air pollution. And the Chinese are actually leading the way now in many renewable technology research. The same in India. And so actually, I think China is taking the lead today when it comes to renewable energies. And they have actually very big plans, the Chinese. They would actually like to connect the whole globe to renewable energy facilities, whether it's solar power, for example, in the Sahara Desert, sell that energy to the Europeans, they've got big dreams, the Chinese, and they may even get there. And so while they are polluting a lot now, they're also doing a lot of research and development on electricity, and the most sales of electric cars are in China at the moment.
And our last question, because we are coming down to that 1 o'clock marker. Would you predict that there could be a massive exodus from major cities because of this extreme temperature disasters?
Well, I don't know about exit. In fact, it may happen the opposite way around. In fact, some people think that a lot of the uprising and the problems in Syria, not from here, started off with a big, very intense drought between 2006 and 2010. There's a very intense drought in Syria, which caused many of the farmers to basically leave their farms because they ran out of water. The wells went dry. They couldn't irrigate their plants. And so climate change may actually have the reverse effect by bringing people from the rural areas into the cities. What happens then is you start to get some overpopulation maybe. You get increased density. Some of those new migrants take over the jobs of the others. This causes friction, and you can get different groups people being recruited by maybe shady groups. And this, people have followed the development of this in Syria, actually, that maybe the drought there triggered or helped to get the whole place, the unrest in Syria, and eventually caused the refugees to leave and to go to Europe. So that's one thing of people actually going into the big cities, but things like rising sea level, like in Egypt, that's definitely going to cause people to migrate, and we're going to see a big problem with climate refugees in the future, especially from countries which are becoming really hot and maybe unbearable in the future.
And you know what, let's just get to this one, because this one's on everyone's minds right now, and hopefully we can nip it real quick.
Sure, no problem.
Climate change, COVID-19. How has COVID-19 affected climate change, for the better or for the worse?
Well, I actually gave a separate talk on this somewhere else, but there are a lot of similarities and differences between the two crises. But on the short term, there's been a positive impact on air pollution. We see this in Europe and in China. People aren't driving as much, not working as much. So definitely there has been a drop, the increase in the quality, the air quality, but it's temporary. Once we go back to normal in a year or so, things are going to go back to normal. And that's the air pollution, which we can actually see, the particles we breathe in, which are dangerous. The greenhouse gases have a very long lifetime, maybe decades, if not 100 years for carbon dioxide. And so I doubt we'll see much of a change in the greenhouse gas. And as it is, if more people are staying at home, they're using more electricity at home, generating more power. So for climate change, there may be a very short-term effect, positive effect, but it's not going to make much change in the long term without doing something drastic.
So all those pictures from Venice, the fish are back, the fish are back. It's only temporary. The fish will be hidden shortly. Thank you so much for sharing with us today, for being here with us. Before we wrap it up, I'd like to pass the floor over to Jeff Hart to say a few words. Jeff, the room is yours.
Well, thank you very much for that great speech, Mr. Price. I always find it interesting because people can get depressed by all the challenges of climate change. But I like to quote this Israeli David Ben-Gurion, who said, in Israel, in order to be a realist, you must also believe in miracles. And not just believe in miracles, take action. JNF has been kind of behind a lot of action in creating the state of Israel against all odds and bringing it to a state today, which was unbelievable when it was founded, that it would be this kind of country in its successes and thriving despite all its problems. And I believe the same can be done, hopefully, with JNF's activity in the field of climate change, leveraging Israel's expertise as a startup nation to bring solutions to market that much quicker. And I look forward to working with JNF on this kind of idea and leveraging all its expertise and innovation and the will of the Jewish people to help commit literal tikkun olam in turning things around in our lifetimes. Okay, so again, thank you very much for the great education. And now we look forward to hopefully helping really speed that curve and make a difference for our children and our children's children.
Great.
Thank you, Jeff. Thank you for Professor Price for being here with us today. Thank you, Karen, President, JNF Montreal, Quebec Region, Galit Levy, the Executive Director, JNF Montreal, Quebec region, Sharon Frankel, Canadian Friends of Tel Aviv University for helping us bridge Professor Price here with us today. Jeff, thank you to everyone again. Again, if you'd like to go back and rewatch, share today's event, it will be posted by tomorrow the latest on YouTube. Just go on YouTube, search JNF Canada. You will find our page. You will find the video. Thank you guys for being here, and we look forward to seeing everybody at our next event.
Thank you very much.
Have a great afternoon, everybody. Take care.
Thank you. Bye-bye.